All right, guys. We're moving on to the second part of this unit, and last week we talked about how delta H, or this change in enthalpy delta H, helps giving us a good guide on how whether or not a reaction takes place, on why it takes place. So we look at the energy changes taking place in this reaction. Today, what I want to do is just continue that discussion a little bit, and then pick up on the last part, the last little clue on how we could study why reactions take place. But first, we'll just take a look at table I really quickly. And table I is just the Regents version of this, or you can look up these values anywhere. But these values are simply the actual delta H values that would occur for the various reactions. So if you take a look at table I, and again, this is happening. If you look at the top here, this would be taking place at your 298K, which is about room temperature, okay, and 1 atm. All right, so you want to make sure that you're highlighting those values when you do this. That has to be defined for each reaction. All right, so if you look at this, you'll see that here's there's your values up there. Okay, so the delta H is going to be written here. Okay, and just understand this value is measured by doing a Q equals MC delta T. So what they do is they do this value for an amount of this material. Okay, and if you look down here, it's very important to know that the values, the delta H values, are based on the molar quantities that are represented in the equation. So if you wanted to burn 1 mole of CH4, you would get this amount of heat, this 890 kilojoules with the minus sign. Okay, so that's important to know. All right, so the first few reactions here are going to be combustion reactions. You'll see basically from methane here down to I guess glucose here would be combustion reactions. And then you have some formation compounds. Now, the way scientists can tell their formation is looking at, an element forming a compound. So you'll see the little F there, means formation, but it's no different than any other delta H. Okay, so these are formation or synthesis reactions. If you go in reverse, those would be decomposition reactions, and you just change the value of the delta H that's here. Okay, the last few down here are going to be physical changes or dissolving equations. Okay, and you'll see the solid salt is here with the S, and that goes to the AQ. All right, and we'll have a little water sign up there telling you that it's dissolving. And again, the delta H value will be measured using a calorimeter, okay, or some other various ways that they can do this. And also, just note the sign. The sign is exothermic if it's negative, and it'll actually tell you down there. So minus sign indicates exothermic reactions, and in a positive sign, it would be endothermic. Of course, if you're going to reverse these, or any of them could be reversed very simply, you would change that sign. Okay, so just a quick summary on this. Okay, so basically what does table I show us? It shows us the delta H for various balanced reactions. Okay, we're going to make sure we treat the delta H as a reactant or a product. So it's important to know that, okay, that when you change the balancing of the equation, you change the ratio of this, you would change also, or I should say multiply the ratio by a number, you'd also be changing the delta H as well. Okay, if it's exothermic, you're going to write the delta H on the right with the products, and if it's endothermic, you're going to write it on the left with the reactants. All right, we'll see how to do that next. Okay, and reactions that form the most negative delta H are the most stable, okay, which means the products are going to be very stable. That's probably a better way to say it. And that's important to know. Remember your potential energy diagram. Okay, if you had a diagram that looked like that, okay, and your diagram was coming up and then coming down, okay, that should be a straight line. Sorry about that. The best it could. All right, the more this drops, the more the endpoint, the more stable you are at the end. Okay, so it's an important way to take a look at table I. Okay. All right. So really, just how do we use the table and read it? Okay, this would be the table again. This would be the bottom of the first page. Okay, let's just say we had the formation of 1 mole of C2H2. Well, we could take a look at the chart, and we'll find that the formation of C2H2 would be this reaction right here, right? And we'll see it's a positive 227. All right, so it would be the endothermic reaction, okay, and the delta H for 1 mole. We want to make sure we check the fact that this is a 1 in front, and of course that's 1 mole, so 1 mole would be 227. That matches your question. Okay, if we're going to find 1 mole of glucose, we'll take a look up here as the combustion of glucose. So we look at the combustions. We see the combustion of glucose is about right there. We're looking for 1 mole. 1 mole is 1 mole. Okay, so then we can take the number right off, and the number would be negative 2804. Okay, it will be exothermic. And also note too the high amounts of delta H's here, how high these are. Okay, because a lot of this energy is released when you burn something, and that's why we use them for fuels. So scientists know exactly what the best fuel is by looking at the actual size of the molecule. You can see here, and that relates to also the size of the delta H. Has some pattern to it. All right, decomposing 1 mole of NO. That's interesting. If I go to 1 mole of NO and I decompose that, I'm going to look for the formation of NO, which is here. Okay. And if I want to decompose that, actually this is wrong. All right, if I'm going to decompose that, I'm actually going to go the other way. I'm going to go backwards. Okay. So I'm going to cross this one out. This is actually wrong here. So remember, formation will be coming forward. I'm going to go that way. All right. So if I'm going to decompose that, I'm going to do, and I only want 1 mole. That's going to have to be an exothermic reaction to decompose. So we're going to go exo here. I'm glad I found that. It's a little mistake. Okay, exothermic. And if I'm going to go exothermic, I'm going to take the 182 and I'm going to have to cut that in half. All right, so I'm going to make that 3489. No, this is wrong too. We'll get rid of that. So what we'll do is we'll take the 1 mole. Okay, we'll get rid of that. That must have been an old problem. We'll get rid of that. Let's do this again. All right, so I'm going to take that 182. I'm going to cut that in half. So let's take 182. 182.6 divided by 2 is 91.3. So we're going to take 91.3. We're going to cut that in half because it's for 1 mole, but we're going to also have to reverse it. So that's going to be negative 91.3 kilojoules. Okay. So that one is a little on the tricky side, but you have to use it. Remember, decomposing 1 mole. So again, what are we doing? We're finding the appropriate equation. This would be a formation going forward. Backwards, we'd have to change the sign and then cut it in half because it's showing for 2. We only want to look at 1 mole. All right, let's make sure my answers are right on this page here, probably because I adjusted a few things. I'm dissolving 2 moles of sodium hydroxide. I'm going to find the hydroxide in dissolving. 1 mole would be 4451. Okay, if I'm dissolving it, of course, that's going to be exothermic, and that's going to be that 4451. But if I want to do that, I'm going to have to multiply this times 2. Okay, so I'll have to adjust that later on. And if I do that, take my 4451 times 2, and I get 89.02 minus. Okay, so that would be the answers to that. All right, so some tricky ones. You just have to make sure you're reading it like again. So delta H is the number that's going with the equation currently balanced. If you change something about the balancing, you have to change the delta H. Okay, so that's that. All right, good job. All right, so really that's how you use it. Just a quick thing on thermochemical reactions. These are actually really easy to do. In fact, you can also do both. You've done both parts of this anyway. All right, so delta H values can be written now. So not only can we tabulate them like we did in table I, but we can also actually write them into the equation. All right, so when we do this, you're going to form something called a thermochemical equation. So we know how to write a chemical equation with the balancing and the reactants and products, but when we add the heat in there, it's called thermochemical. All right, in these equations, the heat will be balanced, okay, with the reaction and is on the right or the left, okay, depending on whether the reaction is endothermic or exothermic. So you have to decide these first, okay, and then you can put the appropriate heat on the appropriate side of the reaction. So for example, let's just say you had an exothermic reaction. Heat is going to be on the right side of the reaction. And let's just say I took this off the table. I had methane plus oxygen, CO2, and water, and I had a delta H of 890. Well, what I would now do is take that 890. If I listed this as delta H equals, if I wanted to write it in the equation and show somebody that was exothermic, okay, I would write it on the right side of the reaction. Okay. Now, when you write it here on the right side, you drop the negative. All right, so the negative is telling you to put it on the right as a product. So that's where the reaction would go. So you don't need the negative when you write it in the equation. Okay. Now for 1 mole, that would be 890. For 2 moles, it will be 2 times the 890 if you wanted 2 moles of this. So the fact that it's written per mole is actually a good thing. You can always adjust that for however much methane you're burning. So you could actually predict this. So let's just say you had 1,000 grams of ammonia. You could take the grams of ammonia. Okay, you could change it to moles of ammonia, right? That'd be easy to do. And then you can change it to kilojoules by using the equation. All right, so there's ways that you could figure out from how much ammonia you have, how much heat you can produce. All right, and that's interesting to be able to kind of figure out. All right, an endothermic reaction is exactly the opposite. Let's just say I had this reaction, and from the table, I was getting 53 kilojoules from the table. So in my table, I was getting this number. All right, and that would be important to know from the table. So what I would do is take that, instead of writing on the right side of the arrow that you saw here up in the top for exothermic, I'm going to sneak it in here before the arrow to show that it goes with the reactants. So this means that H plus I needs 53 kilojoules in order to react. But this is going to make 2HI. So the 53 is already for the 2. So if I wanted 2 moles, then I would use the 53. But if I only wanted 1 mole of HI, then I would have to cut the 53 in half. Okay, so that would be 26.5 kilojoules for 1 mole. Okay, that would be per mole. Okay, so it's really kind of easy. It's just a matter of going through it. Okay, and again, don't forget your endo and your exo. It's a really important concept to know. Whatever class you take, whether you go when you go into next year and whatever. Okay. All right, sounds good to me. All right, so let's move on a little bit. All right, so just a quick note on stability. Okay, when reactions release energy, the product molecules are often thought as more stable. Okay, and that's typically the way it is. So when you do a combustion reaction, you get your CO2 and water. Those are now new stable products. Okay, and that helps us determine why the reaction takes place. You're going to create more stable products. Okay, and this is usually based on their molecular structure. Okay. Some molecules can store more energy than others and exist in a more unstable state. This also can happen. Okay, certain explosives and some fuels are very good at storing energy in their molecular structure and storing how they actually behave, and that's because and their movement. And this is a way they can do this. For example, ATP is a good natural energy storing molecule. Okay, that we use, that all living things use to store their energy and monitor their energy. All right, so usually the rule is this: the more that you release, the more stable the compounds form or the products form. Okay, which do you think is more stable here? If I gave you this one, or if I gave you this one? Okay, if you look at these two reactions, you probably could realize that the fact that you're producing aluminum oxide, okay, produces a lot more heat than what's being produced by carbon dioxide. Again, you just have to be careful of the molar quantities. If you're talking about 1 mole per 1 mole, then you'd have to cut this in half, but that still would be a lot greater the energy. All right, so you'd say that aluminum oxide is more stable because the energy is released is a lot greater. And that's one of the ways you can look at this. Okay. All right, so in this case, another example of here is an endothermic reaction when we're talking about here storing. And we could say that, when carbon and hydrogen react to form this molecule, okay, that it's absorbing 227 kilojoules. Well, you can make the argument and say, hey, if I looked at my diagram would actually be higher. And nature really doesn't favor this, but this molecule has a really good way to store energy. It actually stores a lot of potential energy in its triple bond. Okay, and this triple bond is a really stable source here of storing a lot of energy. So that makes this an energy storing molecule. Okay, and that's what we can often see in a lot of explosives and in a lot of fuels. We'll see this energy storing material within the molecules. Okay. All right, so it's a quick word on table I, not a big deal. And here's a picture of nitroglycerin, which is a really high explosive. Nitroglycerin needs just a little tap and it will explode. Okay, and you can see this really is a carbon compound in the middle, and off the ends are these double bonded nitrogens to oxygens, which are fairly unstable, but they do store some energy. All right, and the last not least is the discussion on something called entropy. And this is the last piece So what we talked about so far is that exothermic reactions typically take place on their own because they release energy. What about some endothermic reactions that take place on their own? How do we handle those? All right, so those are a little strange. So we start off with the statement where, okay, we know that many spontaneous reactions are exothermic and they release energy in the negative delta H's. That's fine. Okay, but some endothermic reactions occur spontaneously at certain times also. How about ice melting? If you took an ice cube right now and placed it on your laptop, you probably wouldn't want to do that. Why? Because it was probably going to melt, right? It would melt into the keys and it would ruin your laptop. But we know that melting of ice is typically something that's going to take place spontaneously, especially at room temperature, right? So how do scientists explain that one when they were explaining for a long time that exothermic reactions were the ones that were spontaneous? How about endos? All right, so we have to look a little further. What happens when ice melts is something that takes place where the particles actually spread out. Okay, and the spreading out of energy or the spreading out of particles to a higher energy state, okay, is called entropy. It's one of the ways we can determine one of the ways we can define the word entropy. So entropy is typically defined this way. All right, it's the spreading out of energy in the system. It's the randomness of particles. It's the complexity of a system. It's a disorder. It's how many degrees of freedom. How many different ways can you organize a system? If you can organize things in a variety of ways, then that is something that has a lot of entropy to it. And the historical symbol for this was delta S. We're not going to do any math with this, but you just want to know what the symbol is. Okay, the math of this involves a small little equation. One of the small little equations, okay, that involve entropy, and this is energy divided by the temperature, would be something called delta S, the change in entropy. And you can see in this picture, you can see that a solid going to a liquid, going to a gas, would increase your randomness or increase your entropy. You can see where this is a more ordered system and it gets more chaotic and the particles spread out a little more as you go. That would be an increase in entropy. All right. Two liquids mixing in a bowl. So this would be a mix. In a solution or mixing would be a good example of something that would be something with more entropy. You can also see it really easy in this picture where a solid is very ordered, liquid is a little disordered, and you have a lot of chaotic disorder in a gas. Okay, as your motions increase of your particles, you become you have more entropy to the system. A good example is your messy room. Sure, if you look around your room right now, it's probably a wreck. If your room is very messy, you would have a high entropy system. Okay, so nature likes this. Nature likes to go to a high entropy system. It's a lot easy to mess up your room and mess up your life and like right now with this whole thing going on. It's a very chaotic, messy situation. Nature intends it to be this way. We don't like it this way, but nature intends it this way. So this is a little clue. And the big idea here, and not to get too crazy with this, is the big idea becomes this. Nature pushes to produce an increase in entropy in the system, or entropy and entropy of the universe. That means the entire universe is always expanding. Nature pushes for this chaotic state. If you take a look at the springtime with all the weeds growing everywhere and everything's like growing rampant, okay, that's an increase in entropy. Okay, nature favors this. All right, so some examples of these increasing entropy idea is very simple. Okay, you want to look at how the particles are spreading out, and the more they spread out, the more you increase your entropy. All right, so you can see a highly ordered system here would have low entropy. A high entropy would be more disordered. So the first example is the formation of a gas. If you form a gas, you would more likely be a more entropy system. So if you take a look at this reaction where potassium chlorate goes to oxygen plus potassium chloride, you could see a solid here that is going to become and has a gas component to it. Becomes a gas and another solid, but it does have a gas component. Okay. In this case, your gas molecules have more energy, so your entropy goes up. Okay, melting and vaporization are good examples of processes where particles will break into a more chaotic state. Okay, your molecular energy, okay, is more evenly spread out amongst the particles. The particles can move, they can twist, they can move around quicker. Okay, a good example would be a solid ice going to liquid, going to gas. So your solid to liquid to gas is a good example of your a good indicator of the fact that entropy is increasing. So really what you're doing is you're paying attention to these little terms down here of your phases, and a lot of times that will help you. Okay, number 3 is dissolving, right? Dissolving to form a solution. Okay, and if you ever wondered why you just place crystals in water and they just dissolve on their own, okay, even though they're endothermic or exothermic, it's because this ion spread out, and as long as those ions can spread out evenly, they will spread out to this to a more chaotic solution, right? And the ions can move around a lot. Okay, good example is a solid going to AQ, going to AQ. All right? And then the last thing really is molecules, small molecules, becoming large complex molecules. If small molecules can get together and form one large one that can spread out energy amongst the molecule, okay, depending on what the molecules and what the atoms are, then you can have an increase in entropy. All right? Okay, so final call here down here, guys. Nature, what is nature really like? Okay, and we're done with part 1 of this unit. Nature loves decreasing enthalpy, or getting rid of its energy outward, okay, and an increase in randomness. Okay, so that would be a negative delta H and a positive delta S. Again, increasing entropy is increasing in randomness or chaoticness of the system. And nature likes both. Now, if both happen, then the reaction is typically spontaneous. A good example must be spontaneous. So a good example of this, again, how we can explain this, is really an explosion. Okay, because explosions are simple reactions that actually do both, right? They decrease their enthalpy because they're exothermic. They produce a lot of heat going outward, but they also produce a lot of hot gas, which increases the chaotic nature of the products. Okay, and so all you have to do is light the firecracker or light the whatever the explosion is, and these things will take place spontaneously. Again, burning is really a explosion taking place over a long period of time, right? It's increasing its entropy and decreasing its enthalpy. All right, so that ends this simple discussion of these two things. Okay, and we will see you later.